What's up, FRT community? So I got a good one for you tonight. I received an email, I don't know, maybe 2 days ago, and the email was, can you help break this down? And when I looked at it, I said, man, this is a good topic. Now, it's not so much related to what you're going to see on the MBRC exam, because they're not going to ask you to do things like this, but they're going to ask lots of questions revolving around this entire exercise. And so if you're a second year student, you're going to want to stick around and watch all of this to the end of the video so that you can see all the ways that this plays in together. Now, what we're talking about here is coming up with initial vent settings when given just a little bit of information. And so you can see I already have it here on the board. I've already written it out. What we have here is a 5'8" male. We want initial vent settings, but we have this specification that we want a desired eye time of whatever it might be. Now, I put in here 0.8 seconds. Now, the email looked essentially just like this. It wasn't 0.8 seconds. It wasn't a 5'8" male, but I'm not here to do your homework for you. I'm here to teach you how to do your homework and how to prepare you and how to know all of these things and how they link together. So let's jump in it and let's figure out what our vent settings are going to be with the desired eye time of 0.8 seconds for this 5'8" male. Now, what we want here is this. This is what everything you should end up with. You should end up with a mode, a tidal volume, a respiratory rate. From there, we're going to give an I time, an E time, an Ide Ratio, and a flow setting. And we only have two numbers to work with. The only two numbers we have to work with right now is 0.8 seconds. So we can go ahead and plug this in here. 0.8 seconds. So we want that. So we know where we're starting. Whatever we put them in, we want an I time of 0.8 seconds. Now, in pressure control, this is real easy because you're just going to set the peak inspiratory pressure and set the 0.8 seconds, and you have your eye time set, and there is no tidal volume set, so that's going to vary in that mode. But we have here specifically being asked for a tidal volume, which tells us that we're going to set that tidal volume. Now, if we set the tidal volume, then that tells us right off the bat that when it comes to mode, we're dealing with volume control, and this is either going to be AC or SIMV. Now, which is better? Don't know the answer to that. I don't like to answer this question. What is the best mode of mechanical ventilation? What I like to answer, or what I like you guys to think about, is what is the best mode of mechanical ventilation for my patient? Well, with this information, we don't even know. So right now, you'll be safe answering AC or SIMV, because we don't know anything else about the patient, okay? Now, we're talking initial vent settings. So let's, from the mode and from the eye time, let's talk about tidal volume, okay? And what I want to point out to you is that we know what the safe initial tidal volume range is. It's 6 to 8 mLs per kilo, okay? So now, I've already done the math here, and a 5'8" male ideal body weight is 154 pounds. You have got to be able to get to ideal body weight. So if I pull up my calculator here, from pounds, we have to get into kilograms because this range is in kilograms. So we do 154 pounds divided by 2.2 kilograms equals 70 kilograms. And we have it there, okay? Now, with that 70 kilograms, we can come down here and say 70. We can multiply it times 6, which is going to be 420. We can multiply it times 8, and we get 560 milliliters. So when we turn that into liters, we're talking 0.42 liters up to 0.56 liters. Okay, now you got to also be able to move between liters and milliliters fairly easily in the field of respiratory therapy. You have to understand that when you say, well, my patient's on a rate of 20 with a tidal volume of 500, and that gives us a minute ventilation of 10 liters, that you don't get confused by that, because 500 times 20 is 10,000 milliliters. We turn that into liters. We talk about minute ventilation in liters most of the time. We talk about tidal volume in milliliters. But these formulas I'm going to show you revolve around tidal volume in liters. So you have to be familiar with how milliliters translates into liters. So we come up here and let's just go right smack in the middle. Let's just go with 0.5 liters. That's what we're going to set for our tidal volume. Okay, now I'm going to erase this because we need this space. So what I want you to understand now is now we have two numbers. Now we have tidal volume and I time. What you must understand from a respiratory therapist standpoint is that if you have I time and tidal volume, then you can calculate flow. If you have tidal volume and flow, you can calculate I time. And guess what? If you have I time and flow, you can calculate the tidal volume. So there's multiple ways to do this. You just have to know one formula. And that one formula is that I time equals tidal volume over flow. And this is in liters per second. That's important because when we talk about flow, we talk about it in liters per minute. But in this case, you have to turn it into liters per second. And this is going to make sense. Think about it. If you have somebody on 60 liters per minute, a tidal volume doesn't last minutes. A tidal volume lasts seconds. And so when you think about it like that, it makes sense that we turn flow into liters per second. And this is really what the ventilator operates off of. It operates in liters per second, not liters per minute, even though we set a liters per minute. Okay, I know that's kind of confusing, but you just have to wrap your brain around it and make it make sense. Okay, now, if we understand this formula, then we understand that our I time here is 0.8 seconds. And that equals our tidal volume. Our tidal volume, we chose 0.5 liters over X. We want to know what our flow is, right? You got several things here you got to solve. And tidal volume and I time will help you figure out your flow. Now, when you do this, you have to get X by itself. So we're going to take it and we're going to put it on, we're going to multiply both sides by X. This is going to give us 0.8. X equals 0.5. Okay, so when we do that, we divide both sides by 0.8. So divide this side by 0.8, divide this side by 0.8, and what we get is X equals 0.5 divided by 0.8 equals, and you're going to get a number that's 0.625. Now, 0.625 doesn't sound like a flow, does it? The thing is you have to remember that this is liters per second. So to get it into liters per minute, you have to multiply that times 60. And our answer here is 37.5 liters. 37.5 liters per minute. Okay? Now, if you're like me, then you see that and you go, wait a second, I thought starting flow was 40 to 60 liters per minute, and you would be right. So we can come over here and we can change some things using this same formula. We can say I time of 0.8 equals tidal volume X, and let's say we want to go with a flow of 40 liters per minute. Then we say 40 liters per minute. Now remember, we got to get that into liters per second, so we do 40 divided by 60 equals 0.666666. We're going to call it 0.67, okay? So we're going to do 0.8 divided by X divided by 0.67. And this is flow in liters per second. Now, what does our tidal volume equal when we set these two things? 40 liters per minute, 0.67 liters per second. All we have to do is multiply both sides by 0.67. This will cancel out, 0.67 over here, and when we do 0.8 times 0.67, we get 0.536 is what X equals. Now remember, X is our tidal volume. So we could easily come over here and say, you know what? If we put them on a flow of 40, we'll have a tidal volume of 0.536. Now if you remember, our tidal volume range was 420 to 560. So this 0.536 means you're going to give a tidal volume of 536 milliliters. So this is still in range, and we can easily change this to 40 liters per minute, excuse me, which gets us into our tidal volume range. And we say, you know what? Instead of 0.5, we're going to go 0.536. And this is liters, 536 milliliters, okay? So now we've got our tidal volume in an appropriate initial vent setting range, 6 to 8 mLs per kilo, 420 to 560. We also have our flow in a starting range of 40 to 60 liters per minute. So now these things are making sense, right? Now from here, you have to figure out the rest of these numbers, right? Well, let's say, how do we figure out E time? Well, to figure out E time, you have to know what your total cycle time is. Once you figure out your E time, you'll be able to figure out your I to E ratio. You can't figure out either of these without knowing your total cycle time unless your E time is given. So if we were given an E time, then we could say, okay, our I to E is this. If we were given an E time, we could calculate a total cycle time. If you can calculate a total cycle time, then you could calculate a respiratory rate. And that's where my next part of this comes. The next point I want after the first point, which is tidal volume, I time, and flow are all related. My next point is that E time and respiratory rate are related. Okay? So, here's how. Total cycle time equals respiratory rate divided by 60. Okay? So, let's just say we want to go with a starting range. Let's say we have a respiratory rate. The starting range is 10 to 16 breaths per minute. Let's just say we want to go with 14 breaths per minute. Then total cycle time is going to equal, I put this up here wrong, I apologize, 60 divided by the respiratory rate. So total cycle time is 60 divided by 14. We chose 14, so we're going to put that at the bottom. Now what this is going to give us is a number, 60 divided by 14 equals 4.28. Now what that means is that the ventilator is going to give 14 breaths a minute. And to do so, it's going to give one breath every 4.28 seconds. Makes sense, right? It doesn't give 14 breaths, just breath, 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 and then stops and waits for a minute to go by. It spreads them out over 60 seconds, which is why total cycle time is 60 divided by breaths per minute. So our total cycle time is 4.28. That means you have 4.28 seconds to get the breath in and then to allow it to come out. In other words, total cycle time equals I time plus E time. See where this is going? We now can calculate our E time here based off of total cycle time and based off of our inspiratory time. So, I'm going to erase this. We know our total cycle time is 4.28. So, if total cycle time equals I time plus E time, then 4.28 equals 0.8 plus X. Right? So, here's what we do. You simply take away 0.8 from here and take away 0.80 from here, and what you're left with is 4.28 minus 0.8 gives us 3.48 seconds. And that equals our E time. Because you see, of this 4.28, 0.8 of it is inspiration, which means the other 3.48 seconds must be exhalation. So we put 3.48 seconds on our inspiratory time. On our expiratory time. So you see how everything is coming together? Now we have one thing left to calculate, and that's our Ide ratio. Now when you calculate Ide ratio, you simply take your I time and your E time, and you put it in ratio format. So you say 0.8 to 3.48. And what this tells you is you're spending 0.8 seconds in I time and 3.48 seconds in E time. But a ratio brings everything back to a 1, to a base of 1. So when you look at this, you're going to actually divide both sides by 0.8. This will give us 0.8 divided by 0.8 equals 1. 3.48 divided by 0.8 equals 4.35. And that's what our Ide ratio is. And what that says is for every 1 part of inspiration, you're spending 4.35 times in exhalation. And that's what it is. So your Ide is 1 to 4.35. And that's your answers, guys. 1 to 4.35. Now, what I want to do is show you another way to get to this same answer, okay? So, what I'm going to do here is erase the 1.4, the Ide ratio, and I'm going to erase the E time, and I'm going to erase the breaths per minute, because I told you that respiratory rate, I time, and E time are all linked together in calculating and developing your Ide ratio. So what if we said we don't want a 1 to 4 or 1 to 4.35? What if we want a 1 to 3? Well, let's see what we get. We can easily come over here and say, you know what? I want to set an I time of 1 to 3, which means I want 3 times exhalation for every 1 part inspiration. Okay, so if we have a 1 to 3, okay, and our I time is 0.8 seconds, and all we have to do is multiply both sides times 0.8. And what we'll get is 0.8 to 2.4. Now, if you want to check yourself, just divide it back out. Divide both sides by 0.8, and you'll get 1 to 3, okay? So 0.8 to 2.4. So this means your I time is 0.8, which makes your expiratory time 2.4 seconds, and that gives you an Ide ratio of 1 to 3. Okay, so we can take this E time, put it here 2.4 seconds, and guess what? You remember what total cycle time formula was? Total cycle time equals I time plus E time. So guess what? Total cycle time equals 0.8 plus 2.4. This equals 3.2. Okay, so our total cycle time, our TCT, equals 3.2. Now watch this. Remember how to calculate total cycle time? Not if you have I to E, then you know you just add those two together, the I time and the E time, you get total cycle time. But I also told you that to get total cycle time, you do 60 divided by the respiratory rate, right? So if we know our total cycle time is 3.2, we can say 3.2 equals 60 over X. When we do that, we solve for X. These sides will cancel out. We multiply this times X, we get 3.2X equals 60. Divide this side by 3.2, we'll get X by itself. Divide this by 3.2, and guess what you're going to get? Remember, respiratory rate turned into X. So when I do this, I'm going to get 60 divided by 3.2. And the answer here is 18.75. So our respiratory rate now is 18.75. Now, of course you can't set a respiratory rate of 18.75. You're going to go with 19. But you understand that that 19 is going to slightly affect your total cycle time and slightly affect your E time, which will affect your Ide ratio. Okay? So I wanted to show you multiple ways to get these numbers, because if I was a college professor, which I am, I would ask this in multiple different ways. I would question you if you know how to get total cycle time in relation to respiratory rate. I would ask you if you knew how to get total cycle time from an I time and an E time. I would ask you if you knew how to get a respiratory rate from an I time and an E time. Or maybe just an I time and an Ide ratio. What's the rate? You can do all those things, and it's absolutely amazing, guys, because it's nothing more than math. You just have to know how to work the formulas. So, I know I did a lot here today. I know I showed you one way, then I showed you another, and things changed. But I just want you to understand that the end answer here is 100% correct. These initial vent settings are 100% correct for a 5'8" male with an I time of 0.8 seconds. Our tidal volume falls within our initial range. Our I time is 0.8 seconds. Our Ide is 1 to 3. That gives us a 2.4 second E time. These two numbers give us a rate of 18.75, and all of that is driven by a flow of 40 liters per minute. I hope this makes sense. I hope you guys see this and go, oh my gosh, like that, I see it, and I see the way these formulas help us to come up with these values. And you understand how flow affects I time, how I time affects flow. You see how respiratory rate affects total cycle time, which affects E time, which affects Ide ratio. That's my goal here. If I did that, give me a thumbs up. If you like this video and haven't already subscribed, please hit the subscribe button. If you're already subscribed but you don't get notifications, turn the bell on so when I put a video up that might teach you just a little something that you weren't already aware of, you know the video's there. And most importantly, I hope everybody's having a great time learning how to be a respiratory therapist or working as a respiratory therapist. Best wishes, guys.